Good morning, friends. By now, you must be very close to asking yourself a question, how much we have really understood about stability augmentation system, right? And if I take you back, when I wrote SAS, this S was for stability, and this is augmentation, and this is the system. The system here is aircraft. What is the meaning of stability augmentation? That also you know now. For example, if I take a pure pitch motion, and you know the equation of motion will be I y y q dot equal to pitching moment, which is half rho v square s c bar into cm alpha into alpha plus cm q into qc by 2u1 plus cm alpha dot into alpha dot c by 2u1 plus cm delta E into delta E. And please understand, we are writing the perturbed equations of motion. Right? These are alpha, q, delta E. These are all perturbed quantities. In the lectures by two of my PhD scholars, they have been using delta alpha for perturbed alpha, delta q for perturbed pitch rate, delta delta E for perturbed elevated deflections. So you should be very clear that we are all talking same thing. And here you also know that we can write this as q dot equal to m alpha into alpha plus mq into q plus m alpha dot into alpha dot plus m delta E into delta E. Then for pure pitch, we have made the approximation that alpha equal to theta and alpha dot equal to theta dot equal to q, and since q dot will be equal to alpha double dot. And by substituting here, we got equation of the form, of course, when I the form alpha double dot, yes, alpha double dot equal to m alpha into alpha plus m q plus m alpha dot into alpha dot plus m delta E into delta E. So all are in now alpha, and you could immediately see they represent similar form of x double dot plus c by m x dot plus k by m x equal to f of t, where f of t force, in this case it is a moment. So we know that we are comfortable, we are in second order system. What is this stability means? We wanted to check whether the airplane, after being disturbed from the pitch like this, whether it is coming down like this or it will go on doing and diverge like this. So who decides that? For understanding that, what we want is, we want something like this. For understanding that, we try to find out what is the natural frequency and what is the damping ratio. Right? You could understand also, by now you are expert, if I go on increasing this zeta, then it damped very fast, right? And depending upon the pilot flying a machine, he will prefer a particular value of zeta and omega n, which is given by the handling qualities requirement. So there is a need to change zeta or omega n in flight, because you know this zeta and omega n, they changes with altitude also, with speed also. So you have to be very smart, so that depending upon at what altitude what is happening to zeta and omega n, I should be able to online augment the stability, meaning they will augment these values m alpha, m q, so that finally zeta and omega n are what we look for. That is the stability augmentation part. And what we have done it in the form of in frequency domain, or using Laplace transform. What we did, we found out the roots S, and let us say for a particular case it has real and complex part with the conjugates. So immediately I know that is going to oscillatory motion. Whether it will diverge or converge depends upon the value of A. If A is negative, you know that it will converge, right? And pictorially, what does it mean? It means that if this is the imaginary plane and the real plane, if I want A to be negative as a necessary condition for the airplane to be dynamically stable so that the oscillation gets damped out, so naturally I expect that this pair should be on the left hand plane of this real imaginary surface. So that this is negative, this part, this real part is negative, okay. But the question is, do I want this root to be here or do I want root to be here? Both are satisfying this condition that real part is negative and it is a conjugate, so naturally there will be a oscillation which will damp out, behave like a second order system. But the bigger question is whether I want the real part to be this much, or this imaginary part to be this much or this much, right? That is extremely important question. And why? Because depending upon this root, these values of omega n and zeta are determined, right? We all know this, how to do that. So in my exercise, when I taught you, what we did, we used the SAS, this is the aircraft. Suppose we want to increase zeta, so the model was like this, and this delta E was equal to KQ. Proportionately, I am deflecting the elevator, proportional to Q, and the moment I do it like this, the CMQ gets augmented, and CMQ gets augmented means the zeta gets augmented. So depending upon whether you want zeta more or less, you can play around here, and how much that you can play around with the value of K. Right? So this is what we did in frequency domain. But you will also understand, my younger friends, they love to work in time domain because they always caution me frequency domain analysis is strictly valid for linear systems, and they want to work in time domain. So what they will be doing, they will write, suppose the equation is alpha double dot minus mq alpha dot minus m alpha into alpha equal to m delta E into delta E. This is typically again second order system, and you all know the characteristic equation for this case will be lambda square minus mq lambda minus m alpha equal to 0, and they will find out the roots lambda 1 and lambda 2. Please understand this alpha means alpha t, perturbed quantity in time domain. We have not taken any Laplace transform. So once they find out the roots, again we find out whether the root is real, imaginary, or complex conjugate, and accordingly they will now tell if I want to change mq from mq1 to mq2, how much delta delta E has to be put. Let us say this is kq. The question is how much the value of k. And simultaneously, if you want to also change the natural frequency, then you know I have to change m alpha 1 to m alpha 2, then delta delta E will have k alpha, k2 alpha, let us say k1. So then the question is, what is k2? Right? So they will be solving it in time domain and make your life very simple, and you will be almost like a machinist will be working to design a stability augmentation system. But remember the word of caution, you can do all these things mechanically, but please understand the moment you talk about delta delta E, how much I can deflect, there is a limitation on the amplitude of delta delta E to be given, which will make the flow the way aerodynamists will like. For example, the flow should not separate. Also the rate, at what rate I am going to change, that also decides the dynamics. So those are the final points, and so please watch out. I think Mr. Prashant and Mr. Dwivedi, Vijay Dwivedi, who have been solving examples and adding value to this course, both of them will be giving you hint how to handle such design of SAS in time domain, right? I again caution you, their notations are different. They are typically control person, we are typically aeronautical person. Although now they are doing PhD in aerospace, there is a problem in this my notation. When I write alpha, small alpha, it is my perturbed quantity. For a typical control person, he writes delta alpha as perturbed quantity. Right? So those notations, I will request them to discuss with you and enjoy this. And I am sure in your assignments they will give some problem. Don't worry about exams and all. You understand this, and so that you can use it in industry. Thank you very much. Now I will request Prashant and Mr. Dwivedi. Okay, thank you.
So far we have studied about the characteristic roots of the equation, the longitudinal mode and your lateral direction modes, and the nature of the roots which we derived from these equations were of somewhere of similar nature, which I am drawing. This was the root location for roll eigenvalues. These were roots of your short period mode. These were the roots for Dutch mode. These were for your phagoid mode, and this was for spiral mode. Now, during our lectures, we saw that the root should be in the left half of this complex plane, represented by imaginary axis, and this is your real axis. Represented by this imaginary and real axis. Now, during this course, while designing our aircraft, the basic requirement was that my plane should be in a stable mode. And as you can see from the roots of this full Sixtov equation of motion, the roots were all in the left half of the plane, so we can say the plane was stable. But what about the requirements of pilot? Or you can say we have studied a lecture on flight handling qualities. Now, as you know, that real part of this roots give us time constant, whereas this complex conjugate gives us the natural frequency and damping ratio. But there are many instances where your damping ratio or natural frequency are not as per your requirement. Say instance, your short period mode, the damping ratio is very less, whereas as per your flight handling quality, it should be a greater value, so that the pilot doesn't have difficulty in modifying your control or giving an additional control to your aircraft. So in that case, there are options to change your eigenvalues or roots of this characteristic equation. One way is either you can change the parameter, but it's a difficult way because you have to modify the dimension and the geometry of the aircraft. Another way is known as stability augmentation system. So today what we will be covering in the lecture is stability augmentation system. Stability augmentation system. As in the name itself, it is mentioned as augmentation. Augmentation means to add something to a system so that it becomes more stable or more efficient to operate. So what we will be doing in stability augmentation system is we will be adding feedback to your aircraft dynamics, so that the value of these roots changes according to your desired value, which you are easy to operate for a pilot. Let me recall the Sixtov equation of motion for an aircraft, which was given by x dot equals to some function of your state variables and an input signal, where your x is your lift, your drag, your moments about x-axis, your y-axis and z-axis. So when we apply the stability augmentation system, what we'll be doing, we will be modifying the state variables with respect to your input signal, and this Sixth-Orff equation of motion can be written as delta x dot equals to df by dx at, as we know that while deriving sixth degree of freedom we used equilibrium position or equilibrium state about which the equation of Sixth-Orff equation of motions were derived. So I can write this Sixth-Orff equation as delta x dot equals to df upon dx at some steady state value represented by x star comma u star plus df upon du at steady state value x dot u x star u star. By this term is known as system matrix, and this term is known as control matrix. As I already told that using this control matrix we will be changing the location of this eigenvalues in the complex plane so that we can reach desired value of zeta or natural frequency or both. Before doing that, let me tell you why we require such stability augmentation system. Suppose for an aircraft, for suppose figure mode, my angle of attack with respect to time changes since it's a second order equation. So we will be getting nature of time response such as response of this nature. Now you can see as it is a second order system, so it will be having a overshoot and a settling time. This is settling time Ts. Now this was my nature of your short period mode angle of attack with respect to time. It will be having some value of zeta and omega n. Now suppose this zeta is very small, that damping is very small, so my obviously the time required to settle oscillation to die out will be very large. But for my aircraft to behave smoothly, the damping ratio should be sufficient enough so that my oscillations die rapidly. So for instance, I want the nature of my graph to die out very quickly. So I want my settling time to this. So for that the value of zeta will be somewhere zeta dash and value of omega n will be omega n dash. So I already told you there are two ways of doing that. Either you can change your aerodynamic coefficient, but it's a difficult process because you have to vary dimension and geometry of aircraft. Another way we are talking is using stability augmentation system. So let us see what will happen when we use stability augmentation system. What happens to your state space matrix? I already told your state space matrix was given by x dot equals to df upon dx at some steady state value of your state variables and input plus df upon du at some steady state value. I call this as standard representation in state space will be given x dot equals to a of x dot delta x plus b of delta u. My state space matrix can be represented by delta x dot equals to a delta x plus b delta u. Now for stability augmentation, I will take a feedback which will be in terms of delta u equals to some k times my some state variables, minus k times of state variable. Now let me substitute this value in your state space matrix. My state space matrix will become A delta of x minus B k delta of x. So delta x dot equals to A minus B k of delta x. Now as you can see, when we use the stability augmentation system, now your new matrix will be A minus B k. As you can see from this new differential equation or state space representation, the roots of this matrix representation, state space representation will be lambda I minus A minus B k, determinant of this equals to 0. So you can say my state matrix representation, the A matrix or state, we call this as state matrix, has changed to A minus B k, whereas for original system your characteristic equation was lambda I minus A, determinant of this equals to 0, which gave me the value of lambda 1 zeta 1 omega n. These were the zeta and omega n for original system, and the zeta and omega n which we required for, or which we preferred over the old zeta and omega n, will be given by this equation. The value of k will determine the new zeta 1 and omega 1 given by zeta say star and omega n star. Now some book, the notation of this k is given as A minus B k transpose. Don't confuse with that. This k can be a single value or in a matrix form given by k1 to kn, depending on the number of states which you are giving as a feedback. Thank you.